we left off last time. What we were doing last time is we were talking about formation constants. And I finished off the class by showing you how to write these things out. So what we're going to do next is we're going to talk about how we can use them. And really, there's only one application that we're concerned about in this course, right? It's pretty obvious from the values of the formation constants that when you mix certain ligands with metals, the complexes will form readily. And again, some of you observed this directly by looking at the iron thiocyanate complex in lab, because basically what you were doing there was calculating one part of the formation constant, because you can add up to 6 thiocyanate ions to an iron 3 ion if you dump enough in. And the formation constant for that complex is actually quite large. But another thing that it can do is it can affect a solubility product equilibrium, and that's what we're going to look at here. All right? So, if we go back to the silver chloride equilibrium that we talked about at the beginning of this section of the chapter, what we saw is that, okay, silver chloride has a very, very low solubility, and you can reduce it even more using a common ion. But there's another facet of this that we have to talk about, and we already have talked about this, at least in one context. Certain anions will be affected by pH. All right, and we talked about that in very qualitative terms. But another way of doing this is by incorporating a complexation equilibrium, and that's what we're going to look at here. And in doing so, what we're going to do is we're going to go back and look at some of the things that we learned way back in chapter 15 as well, in terms of combining equilibria. All right, so here's what we want to think about. We need to look at what happens to the molar solubility of silver chloride if we throw in some ammonia. All right, and again, we have everything we need to quantify this. All right, so we can go and we can look up a couple of things. Now, bear with me for a second. I'm going to go and look at some tables that I created in this so that you can see them on Zoom. Okay, so first, we're looking at the solubility of silver chloride. All right, so we can look up the solubility product constant for silver chloride. And perhaps you remember this because we've used it before a number of times. It's 1.8 times 10 to the negative 10th. All right, now I also have in this set of tables, if I can get to it, come on. There we go. Wait a minute, what's going on here? Sorry. There we go. KF values. Okay, and again, this is basically the same table that I showed you in your notes, and you should have access to from your notes if you want it. And that is that, let me turn the volume down on this. I'm blowing it out. That is, what I can say is the complex AgNH3 2 has a formation constant of 1.6 times 10 to the 7th. All right, that's what I'm interested in here. So let's write those two values down before I forget them. All right, so what we have are two things. The first one is for silver chloride, the KSP value is 1.8 times 10 to the negative 10th. All right, the second thing we want is this. I'm going to cram this down a little bit so it doesn't get obscured by my wonderful picture. For the complex AgNH3 2 with a plus charge, the KF value is given as 1.6 times 10 to the 7th. Okay. Now, why are we interested in that one? Because we're going to have silver ion in a solution of ammonia. And this is the only complex that incorporates those two things. That's another way of thinking about this. All right, so how does it fit into this problem? Well, we can go back to something we learned back in chapter 15, and we can combine these two equilibria. So let's do that. So for the first equilibrium, let's look at the solubility product equilibrium. What does it represent? It represents this: the solid silver chloride in equilibrium with silver ion in solution. And chloride ion in solution. All right, and we know that the Kc for this, which is the Ksp, is 1.8 times 10 to the negative 10th. This is telling us that silver chloride is not very soluble in pure water. We already know that. All right, but now let's look at the solubility product, or excuse me, let's look at the formation equilibrium. All right, we know that the formation constant is equal to 1.6 times 10 to the 7th. All right, we also know that the product of this equilibrium is this complex. All right, that's given to us. You can look this up on the table if you like. All right, it's in solution. And for a formation constant, basically what we're going to do, as we talked about last time, is we're going to combine the two components. We're going to combine the ligand, which in this case is ammonia. So we're going to add 2 ammonias from solution to 1 silver ion, also in solution. All right, now, I wrote these deliberately above one another because the next thing I'm going to do is I'm going to combine them, and I'm going to cancel out anything that appears on both sides in the same quantities. All right, and that's exactly what we can do here. If we combine these two equilibria together, what we're going to see is we have 1 mole of silver ion on both sides, over here on the right at the top and on the left and the bottom. All right, but everything else is going to remain in here. So if we combine these two equilibria, we end up with this: solid silver chloride plus 2NH3 in equilibrium with the complex in solution and chloride ion in solution. Now, how do we get the value of the Kc for this equilibrium given the values that we have written above it? Do we add them together? Do we square anything? Do we multiply anything? What do we do? How did we learn how to do this back in chapter 15? Yes, exactly. We're going to multiply. All right. If this were using state functions, and this is something we're going to go back to in the next chapter, if we're using state functions directly, we would add them. But because equilibrium constants are related to these state functions logarithmically, we end up multiplying the equilibrium constants together. So we're going to take 1.8 times 10 to the negative 10th, and we're going to multiply that by 1.6 times 10 to the 7th. And if I do that, I get 2.88 times 10 to the negative 3rd. All right, so I'm going to round that to 2.9 times 10 to the negative 3rd. All right, it's still small. it's significantly larger, and you're going to see how this affects the molar solubility of silver chloride. All right, so let's set this up. Here's what we also know about this equilibrium constant. We know that it's equal to the equilibrium concentration of the complex times the equilibrium concentration of chloride ion divided by the equilibrium concentration of ammonia squared. All right, that's what we can see from this. All right, just we're writing it out in any other way. So we have a numerical value, we have a mass action expression for it. What are we going to do? Let's set up our ice table. Here's what we're going to say we're going to do in this case. We have some solid silver chloride, and we're mixing it into a solution that contains 0.10 molar NH3. To start with, we have no complex and we have no chloride ion. And so, in order to reach equilibrium, what's going to happen? We're going to have to dissociate X moles of AgCl. And if we do that, that's going to take along with it 2X moles of ammonia. And it's going to form X moles each of the complex and of the chloride ion. Okay, now again, if we solve for X in this particular case, basically what this is going to tell us is how many moles of silver chloride will dissolve into a liter of this solution. All right, even though it's hypothetical and it's not included in the equilibrium expression. And so that means in this case, at equilibrium, the concentration of ammonia is going to be 0.10 molar, or 0.10 minus 2x molar. And each of these concentrations will be x molar. So, our equilibrium constant has the value of 2.9 times 10 to the negative third. And that's equal to x times x, or x squared, divided by 0.1 minus 2x squared, or all squared. Like that. Now, we can't approximate here. X is going to be too large. All right, and again, we could test that out by saying, all right, if we divide 0.1 by 2.9 times 10 to the negative third, we're going to get a quotient of less than 100. All right, so we've got to do something else. Do we have to do a quadratic, though? We could do a quadratic and solve this that way. Is there a way out of doing the quadratic with this one? Yeah. Notice that both sides have, or both components of the fraction have square terms and nothing else. And so we could take the square root of both sides. And that will eliminate us having to solve for a quadratic. Now again, if we do this, we're assuming we're taking the positive root, but that's acceptable, okay? Because if you solve for a quadratic here, you will get a positive and a negative root, and the positive root's the only one that makes sense in the first place. All right, so the square root of 2.9 times 10 to the negative third. I get 0.054. So I get 0.054 is equal to x divided by 0.10 minus x, or minus 2x, excuse me. All right, so I can go further with that. Multiply both sides by 0.1 minus 2x. I get 0.0054 minus, let's see, 0.0542 or times 2 is 0.108x, and that's equal to x. So I can add 0.108x to both sides. I get 0.0054 is equal to 1.108x. So if I divide both sides by 1.108, I get 0.0049 is equal to x. All right, so what does that mean back in the context of our equilibrium? That means that this quantity in moles per liter of silver chloride will dissolve in solution. Okay, so what we could say here is dissolving silver chloride into a 1 molar solution, or excuse me, a 0.1 molar solution of ammonia is going to make the molar solubility of silver chloride to be 4.9 times 10 to the negative third moles per liter. Okay, now think about this for a second. What have we done? All right, if you go back and you look at your notes, the molar solubility of silver chloride in water we calculated to be 1.3 times 10 to the negative fifth moles per liter. So by adding this small concentration of ammonia, what have we done? We've increased that molar solubility by a factor of about 300 or so. In other words, dissolving this stuff into a 10th molar ammonia will increase its molar solubility by 300 times. That's what it's telling us. And this is very useful because back in the bad old days, we used to do a lot of gravimetric analysis with silver chloride. And we used these filter crucibles. We still have them. We don't use them anymore. They're called Gooch crucibles. They're expensive little pieces of glassware. And of course, you want to be able to reuse them after you've used them once. And so the standard procedure was, after we did silver chloride determinations, is we would wash those Gooch crucibles first with ammonia. And what that would do is it would dissolve out all the solid silver chloride. Now, one of the problems with silver chloride is it also photolyzes back to silver metal. Okay, if you leave it out in the light, you'll turn it to silver metal. So another thing you did as a standard procedure for washing was you would rinse with nitric acid to dissolve any silver metal that formed. But this is an illustration of this, and this is something you want to be able to do because it's using the concepts that we've learned in this course. If we combine equilibria like this, all we have to do is multiply the equilibrium constants together. And then we can solve for something a little bit more complex like this. Now I'm going to show you one other example before we're done with, and then we're finished with this chapter. All right, and again, that gives you a week and a half to review everything you need to for the fourth exam. All right, the fourth exam will cover stressing buffers, titration curves, and this material. All right, so let's start out by asking a question that we've asked before. We have a 0.15 molar solution that contains zinc ion. All right, it's zinc nitrate or zinc chloride or something like that. All right, what we want to do to start with is we want to figure out, okay, at what pH will we start to precipitate out zinc hydroxide? And so in order for us to do that, what we need to do is we need to go back to our solubility product table and see if we can find the solubility product for zinc hydroxide. And I see it here. It's 4.6 times 10 to the negative 17th. Oh, wait, no, I'm sorry. That's not the solubility product constant. What is that? That's the formation constant. Let's try one more. Zinc hydroxide. Is it here? Yes, it is. Okay. 1.2 times 10 to the negative 17th. I knew it was somewhere in that range. Okay. So the KSP for zinc hydroxide is 1.2 times 10 to the negative 17th. All right. And again, we can go through and figure out what's going on with this. All right, what are we looking at with this KSP? We're looking at the dissolution of zinc hydroxide. And again, if you don't remember the formula of zinc hydroxide, all you have to do is look at the table, right? Hydroxide ion has a -1 charge, therefore the zinc ion must have a +2 charge because it combines with 2 hydroxide ions to make a neutral salt. All right, we also know that this KSP is equal to the concentration of zinc ion at equilibrium times the concentration of hydroxide ions squared. All right. So, remember what we said about this before. It's a much easier problem to solve because we really don't have to do as much with this. What do we know? We know the value of the KSP. It's given to us, or at least we can look it up. And we also know that in this solution, the concentration of zinc ion is 0.15 molar. All right, so essentially all we have to do is to say, okay, assuming what we've said before is true, that if the mass action expression for a solubility product Q is equal to this value K sub C, then I'm going to start seeing zinc hydroxide precipitating out. So basically what I want to do is I want to figure out what is the concentration of hydroxide ion I need to do this. So I can plug that in. So it's 1.2 times 10 to the negative 17th. And that's equal to 0.15 times whatever the concentration of hydroxide ion is squared. So I'm going to divide both sides by 0.15. I'm going to take the square root of both sides. So I can take the square root of 1.2 times 10 to the negative 17th divided by 0.15. And that's going to give me the concentration of hydroxide ion I need to precipitate this zinc hydroxide out. All right, so 8.9 times 10 to the negative 4th, you say? Okay. All right. So that's the minimum hydroxide ion concentration we need to precipitate out zinc hydroxide. What's the pH of that solution? So from this directly, we can say, okay, what pOH are we looking at? Okay, yeah, let's go. So the pOH would be 3.05, right? And then, yes, as you say, the solution pH would be 10.95 because we're going to subtract that from 14. Okay. Are you sure about that? Yeah, I guess it's... Ah, okay. Yeah, that sounds a little more reasonable. It's not going to be very large. So what does that mean? That means that the pOH is going to be 8.05, right? And so that means the pH is going to be 5.95. Yeah, that seems more reasonable. I would expect zinc hydroxide to start precipitating out of a solution that is slightly acidic, and that's exactly what we're seeing here. Okay, now, here's the thing, and this is something that you have to be mindful about if you're ever trying to precipitate out hydroxides of transition metal salts, like this one. All right, you can say, all right, I want to precipitate out zinc hydroxide. So I'm going to start dumping in hydroxide ion into this solution. Okay, and you'll start to see a precipitate form. And you think, well, okay, I'm going to force as much of it out of solution as I can, so I'm going to continue to dump hydroxide ion into this solution. All right, now here's the problem. This happens with zinc, it happens with copper too, it happens with a number of other transition metals like iron 2 or 3. You keep adding hydroxide, and eventually what happens is everything redissolves again. All right? That's something you have to keep in mind. So one of the things you have to think about when you precipitate out transition metal hydroxides is that you control the pH. You don't get it too high because everything will redissolve if you do. All right, now we could figure that out. At what pH will the zinc ion completely redissolve as the complex tetrahydroxozincate? That would be the name of it. Again, that's not something I expect you to memorize. All you have to do is recognize that what I'm looking at here is a complex, which means I need to look up Kf values. All right, so let's write down what we have so far. We have the solubility product constant for zinc hydroxide. And that represents this equilibrium. And we know the KSP for this equilibrium is 1.2 times 10 to the negative 17th. All right. So now what we have to do is we have to go and we have to look up the solubility or the formation constant for zinc or the tetrahydroxy zinc complex. All right, so there are formation complex or formation values. And we see down at the bottom, ZnOH4 with a 2 minus charge has a Kf value of 4.6 times 10 to the positive 17th. All right, let's write that down. The Kf is 4.6 times 10 to the positive 17th. And depending on where you look these up, I think if you go back in your notes, you get a significantly different value. Let's just see for a second. It's only a couple of pages back. Yeah, it's interesting. Here they say 2.8 times 10 to the 15th. That's interesting. So these things are highly variable depending on where you find them. And that's something you want to think about. All right, so what are we looking at here? We're looking at the formation of this complex. Zinc with 4 hydroxides bound to it. It's got a 2 minus charge as a result. And again, you get that by combining 4 hydroxide ions with 1 zinc. All right. And so, again, we can combine these two equilibria. My computer's doing some strange things here. All right, here we go. We have 4 moles of OH minus in the reactants and 2 in the product, so we can get rid of 2 of them. And so what we end up, and we also have 1 mole of zinc ion in each. And so what we end up with here is an equilibrium that looks like this. We're combining the solid zinc hydroxide with hydroxide, or with 2 hydroxide ions, and we're making the complex. All right, so again, just like we did previously, what we can do is we can calculate the Kc value by multiplying the two together. So we take 1.2 times 10 to the negative 17th. We multiply that by 4.6 times 10 to the positive 17th. Yeah. Okay, we'll use 5.5. All right. So now what are we going to do? Well, here's what we want to think about. This is actually easier than the previous combined equilibrium example, because here's what we can think about. If we start with a 0.15 molar solution of zinc, and we add hydroxide ion, okay? And again, what we're going to do is we're going to go on the assumption that we're not changing the volume of the solution significantly by adding hydroxide ion. What we can say then is this: to redissolve everything, so if we want to redissolve the zinc, what we would want then is this: the concentration of this complex anion is going to be the same as the starting molarity of the zinc cation. All right, now what do we have in the, again, let's look at this mass action expression. This Kc represents this, the equilibrium concentration of that complex. And the only thing that goes in the denominator, the denominator is the concentration of hydroxide ions squared. So, we know the value of the Kc, we know the equilibrium concentration of the complex. Just like we did in the previous example, that leaves us to solve for the concentration of hydroxide ion. So we end up with this. The constant value is 5.5 as we determined. That's equal to 0.15 divided by the concentration of OH minus squared. And so we multiply both sides by concentration of OH minus squared. We divide both sides by 5.5. We get this. Concentration of hydroxide ion squared is equal to 0.15 divided by 5.5. So we can take the square root of both sides, excuse me, and solve for the hydroxide ion concentration. that's what I get as well. So basically what this is telling us is we need a solution that has a concentration of hydroxide ion in it of 0.17 molar. And if we can get up to that molarity, we'll redissolve everything. All right, so again, we could calculate the pOH from this. I get 0.78. And so that means my pH is going to be 13.22. Okay, so that's all I need to say about chapter 17. All right, so we're done with it. And again, that's what you can expect on the next exam, which will be a week from Wednesday.